welcome back to physics online class. So in last class we discussed that effective magnetic moment when that magnet is bent in a different form, when it is bent in a U shape, when it is bent in a S shape, when it is bent at the middle, when two different magnets are joined, opposite poles are getting joined. So if it is joined in a hexagon manner, in all such cases I got that what is the value of effective magnetic moment, right? So in today's session, so we'll have a talk about that magnetic flux and as well as Gauss law in case of magnetism, and also we will discuss about that what is the mathematical expression for magnetic field in case of a bar magnet when that point of observation is on the axial line and as well as on the equatorial line. So we'll start our session with the concept of magnetic flux here. So as I mentioned that there exists similarities between electric field as well as magnetic field. So in case of that electric charge and field, we got that electric flux value, means we got that mean of that electric flux. Just we'll discuss about that what's the mean of that magnetic flux here. Magnetic flux phi of B. What's the mean of that magnetic flux here? The simpler way, the total number of magnetic field lines or crosses are passing through the surface normally, we can call it as magnetic flux. For example, I said that window flux means air flux we can consider, means air flux means the quantity of air which is coming out of that window, so that is air flux. Water flux, the quantity of water is coming through the pipe, that is water flux. In the similar manner, the total number of magnetic field lines are crossing the surface normally, we can call it as magnetic flux. What suppose we have to call that one, so that I can call it as magnetic flux. So how to define it here? The total number of magnetic field lines, magnetic field lines passes through the surface, normally is known as magnetic flux. Magnetic flux you can consider. For example, treat this is one object you can consider. So from this one, the magnetic field lines are crossing here. These are all magnetic field lines, right? These are all magnetic field lines. For this surface, treat this is one surface. For this surface, I will draw one normal line here. Normal line means perpendicular line we can consider. So this is the angle between normal line and magnetic field lines. So I will give that mathematical expression for this magnetic flux. So phi of B, which is equal to integration of B into d of S cos theta. Look at here. So phi of B, which is equal to phi subscript B means magnetic flux here. So integration, surface integration of B into d of S cos theta, where B represents that magnetic field strength, d of S represents that area here, and whereas cos theta represents that angle between magnetic field line and normal line. Look at here. So theta represents that angle between magnetic field line and normal line. Suppose if theta which is equal to 0, cos 0 means, so that is 1. So phi of B will be maximum, so that is B into d of S. If theta is equal to 0 means, what does it suggest here? So if theta which is equal to 0 means, so treat this is one surface here, right? These are all the magnetic field lines. So these are all the magnetic field lines I can consider. So for this surface I will draw one perpendicular line, right? So this is perpendicular line. These are all the magnetic field lines. Look at here. Magnetic field lines and normal line both are in the same manner, means both are same manner means angle between magnetic field line and normal normal line is 0. So this is 0. If theta is equal to 0 means angle between magnetic field lines and normal line is 0. So then flux will be maximum. Now look at here. So this is the situation, angle between magnetic field line and a normal line. So this angle is 90 degree, right? So if theta is equal to 90 degree, if theta which is equal to 90 degree, then cos 90 value is 0. Flux will be minimum, we can consider. Flux is maximum at 0 degree and minimum at 90 degree we can consider. So this is about magnetic flux, we can take it here. Now in case of that electric charge and field, we got that about that Gauss law in case of electrostatics, right? So Gauss law in case of electrostatics, we can consider the total number of electric field lines are passes through the surface, which is equal to 1 by epsilon naught times of the total charge enclosed by it. We can consider phi is equal to, so Q by epsilon naught, we got phi which is equal to Q by epsilon naught. So this is about electric flux. About that electric flux, we got that Gauss law here. Gauss law in case of electrostatics. In the similar way, I can consider that Gauss law in case of magnetic field here. Gauss law in magnetic field. So wait a minute, before going to discuss about that Gauss law and magnetic field, so we'll discuss some SI unit of that magnetic flux. SI unit for the magnetic flux is Weber, we can consider. Look at here, SI unit for magnetic flux is Weber. Right, now we'll have a dimensional formula for magnetic flux, phi which is equal to B into D of S. So theta is equal to 0 means cos 0 is 1. Phi of B which is equal to B into D of S. What is the dimensional formula for this magnetic flux here? Look at here, magnetic force F which is equal to QVB. B shall I write it as F divided by Q into V. Look at here, F divided by Q into V into D of S means, so as it is I will write it here. Now just I will write the dimensional formula for this magnetic flux, right? Phi of B which is equal to force means M1 L1 T to the power of minus 2, right? And D of S means area, that is L square we can consider. Now charge I can take it as current into time, right? This is current into time. I will write the dimensional formula for individual physical quantity. Velocity means L1 T to the power of minus 1, right? So what will be our final answer? Phi of B which is equal to M1 as it is I will write. Look at here, L to the power of 1, L to the power of 2, L cube I can write, T to the power of minus 2 in denominator, A here, A to the power of 1. Look at here, L to the power of 1, T to the power of plus 1 minus 1. So this is 0 here. Then phi of B which is equal to M1. Here that L to the power of 3 is there. If it goes to numerator, so 3 minus of 1, 2. T to the power of minus 2. A to the power of minus 1. So this is the required dimensional formula for magnetic flux. What is the dimensional formula for magnetic flux? M1 L square T to the power of minus 2 and A to the power of minus 1. So this is the dimensional formula for magnetic flux here. So wait a minute, just I will write that dimensional formula for magnetic flux here. So after that we'll have a talk about that Gauss law in case of magnetic field. Dimensional formula. Dimensional formula. What is the dimensional formula? M1 L1 sorry L to the power of 2 T to the power of minus 2 A to the power of minus 1. Okay, so now we'll discuss about that Gauss law in case of magnetic field. So we got that Gauss law in case of electrostatics. In the similar aspect I can define about that Gauss law in case of magnetic field here. So it has some different meaning. In electrostatics it has different meaning, and in case of magnetic field it has a different meaning about that Gauss law here. So what does that Gauss law suggest here? The total number of magnetic field lines crossing the surface is equal to 0, we can consider. Look at here, the total number of magnetic flux passes through the surface is equal to 0, athwa the total number of magnetic flux. So simply we can consider the total number of magnetic flux passes through the surface, flux passes through the surface is equal to 0. Look at here, why I write that total number of magnetic flux is equal to 0 in case of Gauss law? So look at here, phi of B, which is equal to B into D of S cos theta. So this answer is 0. Why that magnetic flux is 0 in case of that Gauss law in magnetic field? But whereas in case of electric field I said that Q by epsilon naught. Why not I take it as here? So here also I should take that value, but here I am saying that Gauss law in magnetic flux I said this value is 0. Why that total number of magnetic flux in case of Gauss law is 0? So why? Because whatever the number of magnetic field lines are crossing the surface or entering the surface, those number of magnetic field lines will get leave out of the surface here. For example, treat this is one surface. From this surface here magnetic field lines are leaving out. How many magnetic field lines are leaving here? That many magnetic field lines will get enter here. Look at here, the total number of magnetic field lines are entering the surface, which is equal to leaving the surface. For example, these number of magnetic field lines are entering here, the same number of magnetic field lines are leaving here. How many number of magnetic field lines will get enter? The same number of magnetic field lines will get leave out from the surface. So that's what in case of Gauss law, the total number of magnetic flux through the closed surface, which is equal to 0. So what does the mean of Gauss law in case of magnetic field here? It implies that magnetic monopole does not exist. Look at here, if magnetic monopole does not exist, for example, magnetic field lines starts from the north pole. From the north pole, how many number of magnetic field lines are enter here? So the same number of magnetic field lines will get from that north pole, how many number of magnetic field lines are emerging here, means coming out, the same number of magnetic field lines will get enter into the south pole here. Look at here, from that Gauss law in case of magnetism, it implies that magnetic monopole does not exist here. So magnetic monopole does not exist means the number of magnetic field lines which is entering, so it is equal to the same number of magnetic field lines which is leaving out of the surface. It implies that magnetic monopole does not exist. Look at here, in case of that Gauss law, we come to know that magnetic monopole does not exist. In case of electric field, I can separate that positive and negative charge, so that's what I can write as phi of E is equal to Q by epsilon naught. But whereas in case of magnetic field, so monopole does not exist. So if it is a magnet means I can take north and south pole. How many magnetic field lines are leaving out of this surface? The same number of magnetic field lines should enter here. The same number of magnetic field lines should get enter here. So that's what I can say, that magnetic monopole does not exist. From that Gauss law and magnetism, so it suggests that magnetic monopole does not exist.